13. Truth tables for complex formulas. There are infinitely many formulas in sentential logic. Nevertheless, no matter how complex a given formula is, we can compute its truth value, provided we know the truth values of its constituent atomic formulas. This is because all the connectives used in constructing A are truth functional. In order to ascertain the truth value of A, we simply compute it starting with the truth values of the atoms, using the truth function tables. In this respect, at least, sentential logic is exactly like arithmetic. In arithmetic, if we know the numerical values assigned to the variables x, y, z, we can routinely calculate the numerical value of any compound arithmetical expression involving these variables. For example, if we know the numerical values of x, y, z, then we can compute the numerical value of x plus yz plus x plus yx plus z. This computation is particularly simple if we have a hand calculator, provided that we know how to enter the numbers in the correct order. Some calculators even solve this problem for us. The only significant difference between sentential logic and arithmetic is that, whereas arithmetic concerns numerical values 1, 2, 3, and numerical functions plus, etc., sentential logic concerns truth values t, f and truth functions and, etc. Otherwise, the computational process is completely analogous. In particular, one builds up a complex computation on the basis of simple computations, and each simple computation is based on a table. In the case of arithmetic, the tables are stored in calculators, which perform the simple computations. Let us begin with a simple example of computing the truth value of a complex formula on the basis of the truth values of its atomic constituents. The example we consider is the negation of the conjunction of two simple formulas P and Q, which is the formula P and Q. Now suppose that we substitute T for both P and Q. Then we obtain the following expression T and T. But we know that T and T equal T, so T and T equal T, but we also know that T equal F, so T and T equal F. This ends our computation. We can also substitute T for P and F for Q, in which case we have T and F. We know that T and F is F, so T and F is F, but F is T, so T and F is T. There are two other cases: substituting F for P and T for Q, and substituting F for both P and Q. They are computed just like the first two cases. We simply build up the larger computation on the basis of smaller computations. These computations may be summarized in the following statements. Case 1 T and T equal F. Case 2 T and F equal T. Case 3 F and T equal F equal T. Case 4 F and F equal T. Another way to convey this information is in the following table. Table 1 P Q P and Q P and Q. Case 1 T T T F. Case 2 T F F T. Case 3 F T F T. Case 4 F F F T. This table shows the computation step by step. The first two columns are the initial input values for P and Q. The third column is the computation of the truth value of the conjunction P and Q. The fourth column is the computation of the truth value of the negation P and Q, which uses the third column as input. Let us consider another simple example of computing the truth value of a complex formula. The formula we consider is a disjunction of P and Q and P, that is, it is the formula P and QP. As in the previous case, there are just two letters, so there are four combinations of truth values that can be substituted. The computations are compiled as follows, followed by the corresponding table. Case 1 T and T T equal T F equal T. Case 2 T and F T equal F F equal F. Case 3 F and T F equal F T equal T. Case 4 F and F F equal F T equal T. By way of explanation, in case 1, the value of T and T is placed below the and the value of T is placed below the. These values in turn are combined by the table 2 P Q P and Q P P and Q P. Case 1 T T T F T. Case 2 T F F F F. Case 3 F T F T T. Case 4 F F F T T. Let's now consider the formula that is obtained by conjoining the first formula table 1 with the second case formula table 2. The resulting formula is P and Q and P and QP. Notice that the parentheses have been restored on the second formula before it was conjoined with the first formula. This formula has just two atomic formulas, P and Q, so there are just four cases to consider. The best way to compute the truth value of this large formula is simply to take the output columns of tables 1 and 2 and combine them according to the conjunction truth table. Table 3 P and Q P and Q P P and Q and P and QP. Case 1 F T F. Case 2 T F F. Case 3 T T T. Case 4 T T T. In case 1, for example, the truth value of P and Q is F, and the truth value of P and QP is T, so the value of their conjunction is F and T, which is F. If we were to construct the table for the complex formula from scratch, we would basically combine tables 1 and 2. Table 3 represents the last 3 columns of such a table. It might be helpful to see the computation of the truth value for P and Q and P and QP done in complete detail for the first case. To begin with, we write down the formula, and we then substitute in the truth values for the first case. This yields the following. P and Q and P and QP case 1 T and T and T and TT. The first computation is to calculate T and T, which is T, so that yields T and TT. The next step is to calculate T, which is F, so this yields F and TF. Next, we calculate TF, which is T, which yields F and T. Finally, we calculate F and T, which is F, the final result in the computation. This particular computation can be diagrammed as follows. P and Q and P and Q P T T T T T T T F F T F. Case 2 can also be done in a similar manner, shown as follows. P and Q and P and Q P T F T F T F F F T F F. In the above diagrams, the broken lines indicate, in each simple computation, which truth function connective is employed, and the solid lines indicate the input values. In principle, in each complex computation involving truth functions, one can construct a diagram like those above for each case. Unfortunately, however, this takes up a lot of space and time, so it is helpful to have a more compact method of presenting such computations. The method that I propose simply involves superimposing all the lines above into a single line, so that each case can be presented on a single line. This can be illustrated with reference to the formulas we have already discussed. In the case of the first formula, presented in Table 1, we can present its truth table as follows. Table 3 P and Q case 1 F T T T case 2 T T F F case 3 T F F T case 4 T F F F. In this table, the truth values pertaining to each connective are placed beneath that connective. Thus, for example, in case 1, the first column is the truth value of P and Q, and the third column is the truth value of P and Q. We can do the same with Table 2, which yields the following table. Table 4 P and Q P case 1 T T T T F T case 2 T F F F F T case 3 F F T T T F case 4 F F F T T F. In this table, the second column is the truth value of P and Q, the fourth column is the truth value of the whole formula P and QP, and the fifth column is the truth value of P. Finally, we can do the compact truth table for the conjunction of the formulas given in Tables 3 and 4. Table 5 P and Q and P and QP case 1 F T T T F T T T T F T case 2 T T F F F T F F F F T case 3 T F F T T F F T T T F case 4 T F F F T F F F T T F 4 3 5 1 3 2. The numbers at the bottom of the table indicate the order in which the columns are filled in. In the case of ties, this means that the order is irrelevant to the construction of the table. In constructing compact truth tables, or in computing complex formulas, the following rules are useful to remember. Do connectives that are deeper before doing connectives that are less deep. Here, the depth of a connective is determined by how many pairs of parentheses it is inside. A connective that is inside 2 pairs of parentheses is deeper than one that is inside of just 1 pair. At any particular depth, always do negations first. These rules are applied in the above table, as indicated by the numbers at the bottom. Before concluding this section, let us do an example of a formula that contains 3 atomic formulas P, Q, R. In this case, there are 8 combinations of truth values that can be assigned to the letters. These combinations are given in the following guide table. Guide table for any formula involving 3 atomic formulas P, Q, R. Case 1 TTT case 2 TTF case 3 TFT case 4 TFF case 5 FTT case 6 FTF case 7 FFT case 8 FFF. There are numerous ways of writing down all the combinations of truth values. This is just one particular one. The basic rule in constructing this guide table is that the rightmost column R is alternated T and F singly, the middle column Q is alternated T and F in doublets, and the leftmost column P is alternated T and F in quadruplets. It is simply a way of remembering all the cases. Now let's consider a formula involving 3 letters P, Q, R, and its associated compact truth table. Table 6 1 2 3 4 5 6 7 8 9 10 P Q R P and Q P R T T T F T F F T T F T T T T T F T T F F T F F T F F T F T F T T T F T F T T T T F F F T T T F T F T F F F T T F F F F T T T F T T F T F F F F F T T T F T F F F T F F F T F T T F T T F F F F F F T F T T F T F 5 1 3 2 1 4 2 1 3 1. The guide table is not required, but is convenient, and is filled in first. The remaining columns, numbered 1-10 at the top, completed in the order indicated at the bottom. In the case of ties, the order doesn't matter. In filling a truth table, it is best to understand the structure of the formula. In case of the above formula, it is a negation. In particular, it is the negation of the formula P and QPR. This formula is a disjunction, where the individual disjuncts are P and Q and PR respectively. The first disjunct P and Q is a conjunction of P and the negation of Q, the second disjunct PR is a disjunction of P and R. The structure of the formula is crucial, and is intimately related to the order in which the truth table is filled in. In particular, the order in which the table is filled in is exactly opposite from the order in which the formula is broken into its constituent parts. As we have just done in filling in the above table, the first thing we do is fill in 3 columns under the letters, which are the smallest parts. These are labeled 1 at the bottom. Next, we do the negations of letters, which corresponds to columns 4 and 7, but not column 1. Column 4 is constructed from column 5 on the basis of the tilde truth table, and column 7 is constructed from column 8 in a like manner. Next, column 3 is constructed from columns 2 and 4 according to the ampersand truth table, and column 9 is constructed from columns 7 and 10 according to the wedge truth table. These two resulting columns, 3 and 9, in turn go into constructing column 6 according to the wedge truth table. Finally, column 6 is used to construct column 1 in accordance with the negation truth table. The first two cases are diagrammed in greater detail below. P and QPR TTTFFFTTF P and QPR TTTFFFFFT as in our previous example. The broken lines indicate which truth function is applied, and the solid lines indicate the particular input values and output values.